Good morning, everybody, and welcome to Physics 4B. Today is Thursday, May 20th. We are finishing chapter 31, basically. We started it, so we're going to finish it hopefully today. We have lab in the afternoon, so I'm hoping that you guys join me for the last lab session. Today is going to be the last lab that we're going to get stuff done, hopefully. In the lab, we have two components in the lab. We have the RL circuit, which we did part of it already when we introduced the inductance. And basically, that is building a current in an inductor. And then the second component of the lab is going to be the RLC circuit, mainly, especially, I mean, in both cases, in the DC circuit power supply and also in the case of the AC power supply. So the lab is quite intensive. There's a lot of work. As a matter of fact, it's two labs in one. So there's a lot of work in it. So hopefully you guys will join me and we go through all of the questions, all of the things that needs to be done and everything else. And hopefully complete it in time before due date, which is May 29th, which is not this Saturday, but the Saturday after, which is in about 10 days from today. So this is what's going to happen in the afternoon. So I hope that you guys will join me for the lab at 5 p.m. This is going to be our last lab. In terms of lecture, we still have to finish chapter 31, do problems from chapter 31, okay? And then, so I expect by Tuesday of next week, we would have done enough problems from chapter 31. Thursday of next week is when we're going to get into chapter 32, excuse me. And then after that, we're done with the content in terms of theory. So we only have to do applications for chapter 32. And in which case we'll put us, and that's going to be January 1st, is when we're going to meet for doing problems for chapter 32. And then after that, you guys have the flexibility to meet again or not to discuss some of the specifics about these chapters. And because we're going to be preparing for the second midterm, the week after, and then we have our final. So this is how things are in terms of all of the things that needs to be done. So because we have quite a few things to do, so I'm going to jump right into the topic that we started last time. So last time, basically, we introduced the inductor, which is actually we introduced it before, and we even did it in the context of an RLC circuit. So basically what I said in here is, so in chapter 30, we introduced the inductor. We said, okay, let's have now a resistor, which is one of the components we discovered first, and then an inductor and a capacitor joined together in what I'm going to call a power supply, an AC power supply, which is really a common thing. Every household has it. Every business has it. And this is how you generate it. So at the end of the day, you've come up with a signal that has either a sine or a cosine, and I make a big fuss over the fact that the sine and the cosine are similar functions. They are actually the same function, shifted only by pi over 2, by 90 degrees, that's all from one another. In other words, there is this trig identity that can give you a cosine as a sine and a sine as a cosine. All you have to do is add or subtract 90 degrees from either one, and you end up with the other one. Okay, so basically I could have done the operation here. Sine of alpha plus 90 degrees is the same as cosine of alpha. So this is basically some trig identities, and that is why when we choose this signal, do not be surprised if it's called a cosine or a sine. That is really most of the time they just give you the angular frequency omega, called it omega prime, and here to make a distinction between a bunch of omegas that already popped up everywhere, okay? We have the natural frequency, which is defined as the square root of 1 over LC, and we have the omega that came up from the transient behavior, namely the fact that there is an oscillation with damping or a damping, pure damping, in both cases where R is very large or R at the critical value that cancels the square root. In all of the three cases, there was actually an exponential decay, at least at the rate of exponential of negative lambda t, where lambda is by definition is also another time characteristic as R over 2L. And that gives me how fast the circuit will decay from whatever it is, okay? So, and then we have the new omega that popped in, and that is because of the signal itself is being generated at a different frequency, which may or may not be equal to any of the other two quantities, okay? So we have to use it as an independent. In general, the frequency and the angular frequency have this names connection between them. And we use Kirchhoff's rule, and this is now how it looks like. So basically, the drop in voltage across the resistor, which is the current times the resistance, the drop in the voltage across the inductor, which is the inductance times the rate at which the current is changing, di over dt, and the drop in voltage across the capacitor is going to be Q over C. Must be equal to the drop in voltage in here in this potential, because I assume during this cycle, because this is periodic, and its periodicity is actually 2 pi over omega prime. So it's pushing the current now here. At some point, it's going to be pushing it backwards. So I took it in one stage so that I can write Kirchhoff's rule. If it is in the other side of the stage, multiply everywhere by -1, and you're going to get the same equation. Mathematically, it's the same equation, okay? So I made some changes in here because this equation has I and Q in it, and I know how I and Q are related to one another. Now I ended up with an equation basically for Q as a function of time. Of course, this is a differential equation. This is not an algebraic equation. And most likely you did not at least start diffie Q, so it's a little bit hard to get going with it. But there is a standard approach to this kind of equations, whether in the mechanical systems, basically, where in mechanics you have a mass spring system and also viscosity, and you also have wind blowing, for example, or something causing the whole thing to move. Then in that situation, this would be an equivalent equation, except the Q is replaced by X, L is replaced by the mass, and R is by the coefficient of viscous damping. And 1 over C is replaced by the spring constant. And then in this case is the force actually that causes the motion, which is supposed to be periodic force. Okay, so if we divide by L everywhere, we are back into our lambda notation, namely that lambda is equal to 2 as R over 2L. And I need really the 2 there for not for cosmetic reasons. So it's much easier for me to write this expression as omega naught squared minus lambda squared. If not, I did not do that, then it's going to be omega naught squared, which is 1 over LC minus R over 2L squared, meaning R squared over 4L squared in here. So instead of doing that, I write it in more concise fashion so that you can remember it. So we put the 2 instead as part of the definition of my lambda. We do that in here. This is still omega naught as we started with from the get-go. Now I have this force in here. So I said in here, then and there, that look, when you close a switch in here on this circuit, when you close the switch, initially there was no charge in the capacitor and there was no current in the inductor. So both of them are 0. But the minute you close the switch, the current starts to flow. So the situation changes now. So there is a transient behavior that happens immediately. And that transient behavior is characterized by that exponential decay. In either of the 3 cases, whether it's overly damped, whether it's critically damped, or whether it's damped with oscillations, this factor, exponential of negative lambda t, or negative R over 2L times t, will kill that behavior, hence the name transient. So this is not going to stay. However, the fact that it's transient doesn't mean that it is not important. It is important because it could cause a lot of damage. It could be associated with a lot of power in it. And that's what you see when you plug in your device immediately into the wall or you unplug it. Both cases, there is a spark actually that you can see sometimes. That, if you don't see the spark, and even if you go gently, there is tremendous transient in your circuit. It needs to be killed off. In order to kill it off, one way to do it is have a huge resistor next to it. That will ensure it's dying off because lambda will be big, and this exponential will go fast to 0. So that is how you handle it in those situations. So there is a transient. And even when you unplug the system or you turn it off, at that time, there is still current in the circuit. The minute you push the button or you pull the power, there is still current in the circuit. So there is still energy in the inductor and there is still charge in the capacitor. So there is still energy in your circuit, in your electronics. So the fact that you open the circuit somehow by unplugging it or turning the switch off doesn't mean that there is no energy in the system. There is still energy, in which case it needs to get rid of it. And usually the resistance is the place where you dump all of that excess energy, and you dump it in the same fashion that you do it in all the time, and that is through the transient. So the transient is important from the beginning, and it's important at the end, but not in between. In the normal operation of the device, it goes to 0, one way or the other. So it's negligible during the normal operation of the device. So what's going on in this case, I have a steady state. The steady state is sustained by the power supply. by this factor, okay? Mathematically, the way you do this is you make this factor equal to 0 and you solve the equations. And that's exactly what we did previously. And then you call that one the general solution of the homogeneous equation. In this case, they call it homogeneous when you put this side equal to 0. So you find it with two constants that depend on the initial conditions, but you cannot apply the initial conditions yet because there is a transient. There is a so-called, in math, they don't call it transient, they call it the special solution. So basically you look for any solution other than that one, and that should fit well. So this is basically how we're going to proceed then. What I'm going to say in here, I'm looking for a solution of this type, that has this frequency omega prime, number one. And its intensity must be also proportional to the voltage that caused it to begin with. So Q must go to 0 when Vmax is 0. In other words, when you open the circuit, when it was closed, so there was a charge in here going on, there was a circuit current and everything else. When you open the circuit, there should not be the steady state. I mean, you go through the transient and everything dies out. The fact that you have the steady state is because of this voltage in here. So the intensity of it's called the response, by the way. So you have system and you subject it to an excitation. And this is the excitation, the external excitation to it. Then the response, which is either the current or the charge or something else, need to be proportional to the excitation. Because if the excitation is somehow lifted, then in this case, the response should not exist. So the response and the excitation must be proportional to one another. So this is what I'm going to say. I'm going to do the following in here. Where's my pen? So this is what we're saying in here. We're saying that the response, which is the steady state, really, steady state, need to be, which is a function of time, by the way, need to be have a Q naught in here in it, or Q max, I should call it, times some, because I took my signal to be a cosine. What is the equation? I have a cosine in here, so I'm going to acquire that this one also better be a cosine. So everybody now needs to be in the same fashion. Of omega prime t, I will allow for a phase shift. I will allow for this one to shift a little, okay? So the frequency is the same. The shift now depends on what's going on. In other words, that could be a delay response, but it's a response nonetheless. So this expresses how soon it will respond. Remember, there is a transient that is in between. So this represents the delay response. In other words, immediately at t equal to 0, we close the circuit. This angle is not exactly equal to 0 at that instant, because if t is equal to 0 at that instant when you close the circuit, there is a phi. You wait another phi for this whole thing to respond. I need to find that phi, by the way. This phi depends on the excitation, and also on my circuit. Namely, it depends probably on R, L, and C, and also omega prime. It could have all of these things together in it. Now, Qmax needs to be proportional to Vmax. The reason why I'm saying that is not equal, proportional. That means it goes with it and drops with it. That means if I make a very strong excitation, that means if I yank the voltage in the circuit upward, very high, I should have a high response. The Q would be very high. If I make it low, the response will be very low. So that's what I'm trying to say. If I kill it altogether, if I make Vmax equal to 0, there is no excitation whatsoever, I should not have a response whatsoever. I mean, there could be the transient, but the transient has nothing to do with the steady state. So this is the whole analysis basically based on the physics that I am having in here. Having said that, this is how my solution needs to look like, then I know what I is. I know what the current is. So the current is going to be as a function of time, which is going to be dq over dt. So it's going to be minus omega prime times q max times the sine of omega prime t plus phi. So this is basically what the current would look like, okay? So this is how the current would look like. I'm gonna write it symbolically, okay? This is some maximum value, that's all, for the current. So I'm gonna write it as minus I max, okay? Times the sine of the same thing plus phi. Basically, I shifted the problem from dealing with a charge to that of the current. Having said that, now this is my current, okay? And if you want to, you can plug in the minus inside and deal with it that way. You're back into this expression here. Let me see what's going on. If the current is some I times a sine of some function omega t. This has nothing to do with omega prime, some periodic function, okay, omega t. If the current is this way, the voltage across the resistor, VR, did we make this analysis? Oh yeah, we did already. We know that the voltage across the inductor is 90 degrees ahead of the current. That is the point I'm trying to make in here. The voltage across the resistor is the same as that of the current, and across the inductor, it's lagging by 90 degrees. So this is how I'm going to represent this whole thing then. If my current is some function, periodic function, this is how I'm going to plot it in here on a circle. This is just to represent the intensities, okay, the relative intensities in here, the circuit. So at some value in here, I have a current times R. So this is the voltage across the resistor, and it's in phase with the current. So this is the voltage across the resistor. It's always in sync with the current. So whatever the current is doing, whatever phase the current is in, the voltage across the resistor is in the same phase because it's just a number R times that current. So if the current is maxed, the voltage across the resistance is maxed. If the voltage, if the current is zero, the voltage across the resistor is zero. If the voltage, if the current is min, that means that the voltage across the resistor is also minimum. So that's basically what this point is trying to argue in here. So that is the same point in here, okay? So the way I'm representing it by a vector whose length is just Ri, where I is the maximum value of the voltage, of the current, okay? This is Ohm's law. So I dropped the time dependence in here. So there's no time in here. That is really how this representation is going. No time now anymore, okay? I'm just looking at the amplitudes, that's all, of the signals. Now, whatever the current is, the voltage across the inductor is going to be 90 degrees ahead of it. So this is my voltage across the inductor. And this, if you look at the expression, it's omega times L times I. Where did I do it? It's the frequency, whatever that frequency happened to be. It's omega prime right now. But in general, it could be any frequency you like. So I'm going to drop this symbol of omega prime because of the fact, let me tell you why I want to do that. Because that omega, the way I define the square root of omega squared, omega naught squared minus lambda squared, and the lambda, the omega naught squared, which is 1 over square root of LC, omega naught is 1 over square root of LC. Those two, they really depend on the they describe the transient. And since we already are we ignored that. In a sense, we waited too long for it to go away anyway. So we don't care about those symbols. So I'm going to go back just to simplify the notation so that I'm talking about the frequency in here. But the point in here that you need to remember is that this omega I'm about to write is that of the excitation, is that of the power supply. So this is omega times L times I. So this is the voltage across the inductor in its maximum value. Where this omega, it's very important to remember that this is from the power supply. It has nothing to do with 1 over square root of LC or square root of 1 over LC minus R squared over 4L squared. No, This is the actual omega, the one that from the power supply. It's just basically convenience node to drop that omega prime, that symbol in it. If in doubt, go back into it, okay? Now, so this is above 90 degrees ahead of this current. Whatever the current is doing, this guy is ahead of it. This one is in sync with it. Now, across the capacitor is actually equal to 1 over omega times C times I. So this is actually, so this is 1 over, this is VC. This is the voltage across the inductor. Now, this is 90 degrees behind the current in the opposite direction, basically. And that is how I'm representing this, basically using vector notation. This representation is called the phasors. Okay, you write it this way, okay? It's the same thing as writing this whole with the sine and the cosine and adding 90 degrees to it and subtracting 90 degrees to it. So it's the same notations in here. This is omega times L times I, and this is the sine. So this whole thing is just the temporal behavior, and this is some pi over 2, plus pi over 2. So instead of doing that, I just dropped the amplitude only. So I'm representing only the amplitude, only amplitudes. In other words, this whole thing is spinning actually. It's going around this way, okay? At the rate of omega, which is the signal that caused it to begin with, okay? Now this is a vector notation. So I need to add all three of them to actually find the actual voltage. So what I'm going to do in this thing, I'm going to take, because these two are on the same axis, which is the y-axis, but one of them is pointing north and the other one is pointing south. So I need to find the difference between them. Let's say, for example, this is the difference between them. So this is VL minus VC. Excuse me. So the entire voltage across the circuit must be the sum of these two vectors, basically, which is this vector. Okay? And this vector is clearly, from this notation, the entire voltage, which is the voltage across the circuit, actually, must be equal to the square root of VR squared, using the Pythagorean theorem. So this quantity squared plus this quantity squared, VL minus VC squared. That's it. Whereas in this case, I know what this quantity is. It's just R times I. So let me change the pens again. So this then voltage, this is the entire voltage from the battery. Must be equal to the square root of Ri squared, both of them squared because the R needs to be squared from the Pythagorean theorem, plus, open parenthesis, this number is just omega L times I minus I over omega times C, the whole thing squared. Obviously, I have an I squared in here, and if I took an I in here and an I in here, it's going to be an I squared. So I will have an I squared everywhere, which I'm going to yank out of the place in here. So V looks like it's equal to square root of R squared plus omega L minus 1 over omega C squared under the square root times I. This looks like V equal to Ri, except I don't only have an R, I have a bunch of stuff in here. So I'm going to write this one symbolically as Z times I, where Z by definition in this case is the impedance of the circuit. Z is the impedance of the circuit. So it looks like it's Ohm's law. Like Ohm's law. This would be an Ohm's law, but this is basically the version that we ended up with in here. So basically, this is the value for the impedance, in this case for the circuit. Now let's define a few things in here. I'm going to define XR as the reactance of the resistor, and it's R itself. So XR is the reactance, or the resistor reactance, and the resistor reactance is just the resistance. the units for this guy is an ohm. I'm going to define also XL as being omega times L, as you can clearly see from this expression. This is omega L. So I'm going to call this one the inductor reactance. And this too has the same units as an ohm, because it's multiplied by current, amps. In the original expression, what is it? When we took it out, way up here, omega L times I gives me a voltage, because this is a sign has no units. It's a sign is a dimensionless number. It's going to be a number between 0 and 1, and between -1 and 1. So this has the same units as an ohm also. The same thing I'm going to call capacitor reactance as simply XC equals to 1 over omega C. So this too has the units of an ohm. All of them have an ohm. As a matter of fact, Z itself has the same units as an ohm, because it's the square root of XR squared plus XC minus XL, or XL minus XC. Usually I write it this way. Okay, I know it's squared, so it doesn't matter which way you write it. Squared. This too has the same units as an ohm. So even the impedance itself is some sort of resistance. So they all have the same units in here. Having said that, now my circuit look like this then. I have a power supply, which is an AC power supply. This is its maximum. I have a resistor now that is acting as a resistor, as a reactance, which is like a resistance really. I have an XL in here, whose value I know what it is. I have an XC in here, and from there, this is basically how the circuit look like. So if I want to apply Kirchhoff's rule now, what I'm saying in here is this is how the new rules are. If you encounter an R, you're going to leave it as is. If you encounter an XL, you have to shift it by 90 degrees up. If you find an XC, you have to shift it by 90 degrees down. So if I apply Kirchhoff's rule in here, this tells me that the current I is given by the voltage divided by the square root of, because I have to apply the Pythagorean theorem now, of XR squared plus the difference between, because one of them is up and the other one is down, of XL minus XC squared. And that is the end of it. So this looks like it's Ohm's law. And this is exactly now what the response is. So this is I. And we started with the premise saying that the response, which is the current in this case, and the current, its integral is just the charge, and the charge in this case need to be proportional to V, and they are, because with the exception of Z in the denominator, this is what V max is. So if I'm looking at the I max, this is the maximum current, that is the response. So this is my response, and this is my excitation. So indeed, it is how I expected. That is one thing. The other thing, if I go back into my geometry in here, I see that the voltage across the entire circuit and the current are out of phase in this case. It seems like the current is, the voltage across the circuit is leading the current by this angle, phi. So the current is basically lagging behind the voltage in this representation, because I assumed that XL or VL is bigger than VC. Because if it was the opposite in here, if this vector was much bigger than the other one, then in this case, actually the current will be ahead of the voltage. So let's first of all find the tangent of this angle. It's clearly from the tangent of this angle, it's VL minus VC divided by VR. It's the opposite over the adjacent. So the tangent of phi from the geometry, tangent of phi, is equal to the difference between VL and VC divided by VR. Obviously, this one is equal to XL times I minus XC times I divided by XR times I. Cancel all of this I's. Or if you wish, the tangent of phi is omega L minus 1 over omega C divided by R. Either way, this is the phase shift between the current and the voltage. the voltage across the battery. Okay, so in other words, the current lags behind. So yeah, exactly how we described it. It's actually behind. So in other words, the voltage comes in, kicks in the circuit, and the response, which is through the current in this case, and so we're analyzing the current looks like it's not in sync with it. It's slightly delayed, and the delay is this angle phi actually. If, and it's a big if, omega L is greater than 1 over omega C. So when omega L is bigger than 1 over omega C, then it's true what you're saying. That in this case, the voltage leads the current. Or if you wish, the current lags behind the voltage. Okay? Now, if the other way around, if actually omega L is less than 1 over omega C, clearly this angle is negative. I mean, this number is negative. So in this case, phi would need to be negative. If phi is negative, then in this case, the voltage actually lags behind the current. Here is the scenario. When you're going too slow, okay? When you're going too slow, so you push it, and now, basically in this case, the voltage is always ahead of a response. But when you're going fast, dragging something in here, you go in before the other one catches up with you. So that's basically the scenario in here of what's going on. Now there is a frequency where this numerator is exactly equal to 0. When omega L is equal to 1 over omega C. In this case, phi is equal to 0. Okay. When phi is equal to 0, who is ahead and who's behind? There is nobody who's ahead and there is nobody who's behind. They're in sync. So in this case, neither is ahead and nor is behind. As a matter of fact, I can solve this equation for omega. I can say omega squared is equal to 1 over LC. Remember, 1 over LC is omega naught squared. So that means when omega is equal to omega naught, which is the natural frequency of the system, we have this situation. We call this situation resonance. Okay, for very large values of omega, for extremely large values of omega, in that case, 1 over omega becomes small. And this value approaches infinity if omega is truly large. Then in this case, the arctangent of infinity is actually pi over 2. So that is completely out of phase. If one of them is cosine, the other one is sine. That is basically what that means. When omega is extremely tiny, extremely small, this number is negligible because it's tiny. Omega is tiny. But dividing by a tiny number becomes very large. So in this case, the value is very large still, but it's in the negative sign. So it's going to negative infinity. So it's still now, it's a negative pi over 2, because the arctangent of negative infinity is actually negative pi over 2, or 270 degrees. So in this case, so those are the two scenarios that we're looking at. So let me draw how the function pi depends on omega, actually, because if I can play around with omega, then I have this leeway. So let me draw the thing in here. So this is omega naught. This is where resonance happens. In this case, the angle phi is exactly equal to 0. For very large omega compared to omega naught, the value approaches pi over 2, 90 degrees. For very tiny values, namely omega is very, very small compared to omega naught, practically 0, then in this case, the angle phi will be negative 90 degrees. In other words, the voltage will lag by almost 90 degrees behind the current. So the current will be ahead by 90 degrees. So this is how this function look like. So it goes through transition right around the resonance, and then there is a deflection point in here, and then it goes back into negative degrees. So this is where the resonance sits. Resonance. So this is basically what I was talking about in terms of response and delay and ahead and all of that. So there is definitely not in sync situation. It's only in sync when omega is equal to exactly omega naught. So if you're playing around with omega, then you can do that, okay? Let me look at the current now. The current, remember, is equal to V divided by the square root of R squared plus, I'm looking at the max value, okay, for right now, plus omega L minus 1 over omega C. I'm going to do several mathematical manipulations of this expression in here to put it in a something that I can manipulate, okay? One of them is the fact that we defined R over 2L to being lambda, and we defined omega naught to be 1 over square root of LC. In other words, omega naught squared is just 1 over LC. So for that, I need to take advantage of this situation. So I'm going to put divide by L in here and multiply by L. So in other words, I will have an L squared in here and an L squared in here. And plug in the L in here, 1 over L squared is going to cancel this L. Because remember, when I enter it inside, it's going to be just L. So it's going to cancel that one. And in here, it's going to be omega naught squared. Furthermore, I'm going to multiply also by omega squared and divide by omega squared. Let me tell you why that is. Okay, in this expression, the omega squared that I'm going to introduce is this one, the one in the numerator. When I do that, it's going to be just omega. It's going to cancel this omega squared in here. I should have done it the other way. Sorry. In the numerator, I'm going to introduce. So this one is true. I'm going to introduce omega naught squared, omega squared in here. So let me pick up a pen in here so that you guys are following if you're going to do the algebra. So I'm going to enter omega in here, so it's going to simply be omega. So it's going to cancel this omega, and there will be a square in here that's going to appear because I introduced this one. So I'll have an omega squared in the denominator. Furthermore, I'm going to take also the L squared, or not the L squared. It has to be C then if I'm going to do that. So this is going to be C squared, not L squared. And I'm going to do also the C. Don't worry about it, okay? So I'm going to do the C squared in here. So when it enters, it's going to be C in here. That cancels this C. So I'll be left with 1 in here because everything cancels in here. But then I will have a C in here. And C times L is exactly 1 over omega naught squared. That is what LC is. So we'll have an 1 over omega naught squared in here. So we'll have omega squared over omega naught squared in here. So that's going to appear in there. So this is basically what it will look like, this expression. Minus 1. The whole thing is squared, don't forget. Multiplying, so I entered this one, and I entered that one, so it's going to be multiplying 1 over omega squared C squared. So that's the thing that's going to stay in here in this expression. I'm going to take another look at this expression in here and take this as a common factor completely out. Meaning I'm going to multiply and divide by omega C over omega C. This factor will go in. So when it goes in, it's going to be squared. So there will be an omega squared in here times C squared in here. And this omega C will come out completely out in here. What happened to my L? My L was consumed in here. That's fine. That's fine. No big deal. Okay. So I will have C squared, omega squared in here, but then it will cancel this term in here in the second one. That's exactly why I took it out. And then it's going to go on the numerator. So this is how the expression would look like if I do this calculation. And hopefully you guys were able to do it too, because I need to draw this function here. So what I will have in here, I will have I max equals to, this was in the denominator, so it's going to go up there. So we'll have C times V max times omega, okay, divided by, oh, there is the term I was looking for. I thought I lost something in here. So I will have an R squared, C squared times omega squared plus omega squared over omega naught squared minus 1, the whole thing is squared. That's all what I will end up with. Furthermore, I need an omega naught squared in here in the denominator, because I want to express this in dimension. What I'm doing, I'm rescaling my problem. And this is a typical behavior that we do in physics. We rescale the problem so that we can plot it correctly or analyze it better, okay? So I'm going to have, because I need to draw this one as a function of omega over omega naught. I don't want to draw it as a function of omega by itself because I will have a bunch of parameters in there. So I will need omega naught squared. In other words, I need to multiply by omega naught squared, and omega naught squared is just 1 over LC. And this C and that C is the one that cancels. That's why I was worried for a moment about what happened to my LC. Okay. In the same fashion in here, I'm going to divide by omega naught and multiply by omega naught. And omega naught itself is 1 over square root of LC. So having done that, and hopefully you guys have followed, if not, please rewatch this one and go through the steps. This is how the expression looks like now. Imax of the current looks like it's this square root of C, and this C will leave me with another square root of C in here. So there will be a Vmax, definitely a Vmax, times the square root of C over L times omega over omega naught. That's exactly what I was looking for, divided by the square root of R squared C over L times omega over omega naught, the whole thing squared, plus open parenthesis, open another parenthesis, omega over omega naught squared minus 1, the whole thing is squared. So in rescaling my problem, I'm going to define my function y as Vmax, sorry, yeah, Imax, I'm sorry, as Imax divided by this constant in here, because this is just Vmax times square root of something divided by something. So it's Vmax times the square root of C over L is equal then. So this is gone. And I'm going to call X equals to omega over omega naught. So this becomes just X I have in the numerator divided by. And at the same time, for the sake of this whole analysis, I'm going to call L squared as simply being R squared C over L, this number in here, because I want to plot it in terms of this parameter. Look how the expression now looks like. So the function I want to plot is this function. So I only have one parameter only to worry about, namely L squared. Everything else is rescaled. In other words, this function will be dependent on X. So for X equals to 1, that means omega is equal to omega naught. That's all. For Y equals to 1, that means Imax is equal to this whole thing. That's all. So I rescaled my problem. In other words, I adjusted the units on the X-axis and the Y-axis so that I have only function that depends on X. So let me plot this function now, because it's a very important function. This is something that probably the first time that you're going to see it done correctly, and later on they will refer to it, whatever class you're taking, engineering, chemistry, physics, other places. So I really want you to have a feel for it. So I'm going to stop sharing that screen. I'm going to go and plot this function for you guys, and hopefully we'll have a discussion on it. The book has that same discussion, but it's discussed in one basically place that is, I really don't like it, honestly, one page. So let me share with you the calculator, and let me come to the graphing side of it, and let me enter my function y the way I have defined it. So y is equal to, first of all, the numerator has only x in it. The denominator has the square root of, open parentheses. So I called it L because I want to write lambda, but I really don't want to write lambda the whole thing. So I just want to write L. So it's an L squared, and because it's a positive, that was actually the value related to lambda, because it's related to the resistance. So that controls the that's controlled by the resistance basically. That value, if I make it bigger or smaller, is I'm just playing with the resistance. So it's an L squared times x squared plus, open parentheses, x squared minus 1, close the parentheses, and the whole thing is squared, and the whole thing is under the square root. So this is how the function then looks like. Let me double click on it to make sure I didn't make any mistakes. This is exactly the function I want to plot. X is positive because omega is between 0 and infinity. So frequency can only be 0 at extremely basically non-oscillating phenomenon where the behavior is linear and then fast going to infinity. So that is the control in here, the variable in here. This is the independent variable. Y is the current now, maximum current. basically how big the current is going to be depending on X. So I'm going to enter it again, and I'm going to graph this function. Obviously, this calculator doesn't know what I'm doing. So right now it's taking forever to do this graphing. Okay, so it gave me a plot in here, both in the negative and positive. I don't like that. So I want it actually to be in the positive region only. And I know also that my Y starts from 0, except the range, I'm going to make it big. I'm going to make it, let's say, for example, 20 seconds, because the 20 seconds, 20 omega knots, okay? So the biggest value is going to be around 20 omega knots. So let's make it 15 omega knots. And the maximum value, let's control it to about 5.5 or 5.2, okay? Because I want to make a change in here on my graph where this B, I know it can be very small. So I'm going to make it as small as 0.2 and as big as 4, okay? Or let's make it 5. Okay, that's fine. So this is the values for L that I can change. If I change L very fast, so what is allowing me to change is L, not L squared. So for very low resistance, look at the curve, how it behaves. It's peaked, and its peak value is actually 2, 4, 5, which is the inverse of this number, basically. Okay? It's not exactly 5, it's 4 point something, which is about the inverse of this number. If I make it larger, the maximum drops, and it drops until it goes basically, practically there is no peak in here. Where does it peak? It peaks at the value of X equals to 1. That is omega naught. That is at resonance. At resonance, the response would be at its maximum. So this is the resonance curve. At very high values of lambda, meaning the resistance is very, very large in this case, you don't hardly have any peak in here. You have the peak, and this curve opens up, it broadens. So if you have a broadcasting station broadcasting at this frequency in here, and you would want to have a signal, you need it to be narrow around it, because if there is another station broadcasting in this region, guess what? You're going to pick up that station with this much current in it, with this much intensity. Whereas, of course, the one that is broadcasting will be your main dominant one. But if the next one is here, for this curve, it's not going to pick it up at all. But this curve will have a problem, because this curve in here will pick up almost all of them with the same intensity. So this, you will have a nonsense signal, because you will have all of the other stations broadcasting at the same time for you. So if you really want to have good reception, you would want to tune your device to this frequency in here. Obviously, the maximum actually shifts too. Look at the maximum now. For large values of R, it shifts slightly less than X equals to 1, namely omega less than omega naught. And it only peaks at its best around X equals to 1, which is this value, around this value. And it's always equal to something divided by the resistance. The smaller the resistance, the higher the peak. As you can clearly see from this parameter in here, the higher the resistance, you cannot see even the peak at all. Obviously, for very, very less x's, which is X equals to 0, the numerator cancels. For X equals to 0, this is 0, this is 0, this is 0. So you'll be left with -1 squared. So it's going to be basically 0 divided by 1, which is 0. For very large values of X, for very large frequencies also, this is going to infinity. This is going to X squared. When you square root it, it's going to go infinity. So you have an indetermination of the forms infinity over infinity. But don't forget this term now. That dominates actually the denominator. X squared will be a lot larger than 1, which makes this X squared to the power 4. X to the power 4 is larger than X squared, no matter what L is, no matter what R is. Then in this case, you're going to be square root of X to the power 4, which is X squared. And X squared is a lot less, a lot more dominant than X. So the whole thing drops like 1 over X. That's exactly what you're looking at in here. For very large frequencies, in this case, the signal basically becomes insignificant. So during the resonance is when this curve has significance in here for very low values of R. For very low values of R, This is basically what this thing is. The quality factor for a resonance curve is usually when you take the max value divided by 2 and you solve the equation for it. You'll find a line in here somewhere. You will find that this one broadens with R. In other words, when R increases, the quality drops of the resonance. The reception becomes not good. When R increases, decreases in value, the quality factor becomes a lot better because that factor region becomes narrower and narrower, which means that you can use it for your signal. This is because we only have one omega naught insert. Imagine with me that we have a bunch of omega naughts now. Then each one of them will have its own peak, and its peak depends on the properties that you have in there. That is how resonance is actually used in spectroscopy to do spectroscopic analysis of materials. You use it also for that purpose too. You send an excitation, you heat up the material, for example, and you put it in the sample. Now everything starts to go back into their ground state in terms of the energy, and they will go with specific frequencies depending on the intermediate transitions from one level to another level to another level, and you're going to pick up those frequencies specific for that element. So this resonance is tremendously powerful stuff. Make sense to you guys?
Yes, it does.
Yes.
The L is sorry if I'm wrong on this, but L is representative of resistance, you said? Because I'd heard resistance would be the L in this whole thing. When it's more resistance, it would be more dampened, or not dampened, but a smaller value for that giant peak.
Let me show you where we got the L from so that we have no F's or buts about this one, so that it's 100% clear. Okay, this is L squared. It's basically R squared times the square root of C over L. C and L really control that omega naught. Remember, omega naught is 1 over square root of LC, okay? So in other words, yes, you're right. You can play around with the L by changing C or L a little bit, but that's not how we do things. We do it just with R, because it's proportional. L and R are proportional to one another, because L squared is L squared, R squared. Make sense?
Okay. Yeah, I see it now.
Okay. So and omega naught, which is part of the definition of X is omega over omega naught. Omega naught was all along 1 over square root of LC, and that's how I arrived to that expression here. Here is my omega naught. So basically, if I am at resonance, the phase, they're in sync. And in this case, this curve is at its maximum. I would love for you guys to draw that graph too on your own, okay? If not, please refer to the book so that you understand where these things are coming from, because it's very, very important, powerful stuff in here for you guys, okay? So this is really one of the most important topics that you're going to learn from this chapter. And resonance in here plays a major role in a lot of branches of science, whether criminology, whether doing, for example, analysis of materials, you look at the galaxy, for example, and the light collected on the telescope. Of course, it's not visually analyzed, usually analyzed by a computer, goes through the point where it's collected first from the big mirrors, then goes through a reflector, and that reflector goes through like a diffraction grading and material like this one, like this thing in here. And then when it's broken down in its components, then the computer will look for those frequencies, the max frequencies that are coming into it. Based on that, you can determine the composition of a star billions of light years from here. Galaxy billions of light years from here, or a star thousands of years light from here, or even planets. We do that for them to see what are they made of, how much hydrogen do they have, are they first generation stars or not, how much helium do they have, how do they know? Nobody went to anybody. No, we didn't even go to our own star, let alone to a star like any star, doesn't matter. But we do that. How do we do it? This is one way of doing it. This is actually the only way of doing it, okay? That's how you know things about things, okay? Somebody was murdered, and arsenic was suspected. So you take the sample of his, basically, whatever tissue from wherever you're supposed to have and then you send it to the laboratory. Again, they excite the material. Once they excite, the first type of a spectrum that I was talking about is a type of a spectrum that is usually called there are two types, absorption and emission spectrum. Spectra, in the case that I'm mentioning now, it's actually an emission spectrum. You excite the sample, you heat it up, or you put it under high voltage or something like that. You know that it went to a higher energy levels. And then as the atom starts to relax back into their ground state, then, or the molecules themselves start to relax back to their own ground state, they emit light. They emit basically different frequencies, the signature of their own unique things. So if you look at them, then you can tell exactly what type of material it is. And again, you use this is resonance because you excited the material, and now the response which you're collecting is going to go peak at certain frequencies. So that is exactly how you're going to do the analysis in this case too. It's a similar fashion in a sense. It's a resonance of some sort. Okay. So this is extremely powerful stuff. We still have a very important topic in here to talk about, and then we close the book on this chapter, and that is the power, because it doesn't make any sense until we do power. I mean, it's not as important until we talk about the energy. Where is my pen? Okay, power. So you guys remember from way back that the power in the DC circuit basically turned out to be the voltage times the current, okay? In the case of Ohm's law, it's Ri squared. So this is in the DC circuit. But in here, we have time dependence behavior. So let's imagine together that somehow this is my voltage is some sort of a sine or cosine, it doesn't matter. So we're gonna start with Vmax times some, for simplicity's case, because I really don't want to deal with the negative signs, and it's the same thing anyway. So it's a sine of omega t. This is the source, or the power source. Now, the fact that I wrote omega in here, and I already mentioned several warnings about this one, this is the power supply omega. And we already have a bunch of omegas in the circuit, so please pay attention to each and every one of them. There will be immediately 4 problems that we're going to tackle specifically about this circuit from this chapter on Tuesday. So please join us on Tuesday so that you see firsthand how these things are, okay? So that you can, because you will never learn these things unless you practice them. They will never sink unless you practice them, unless you do problems. And you do them, don't watch me do them, just follow and do the things that I'm doing with you so that you can actually have better understanding, better grasp of these things. Otherwise, it will never sink. And I'm afraid that's going to be your loss, because this is your opportunity for you to get these things once and for all. Okay, so this is the power supply, okay? Then the current is somehow, so this is, I'm sorry, this I should write it as a V of t now, because this is a function of time. Remember, this is the EMF now, okay? So the current now, which is some function of current of the time, which is I max times the sign shifted by a value phi, okay? So we argued how to find phi, and we argued how to find I. As a matter of fact, phi, tangent of phi, is equal to XL minus XC over R over XR, or if you wish, it's omega L minus 1 over omega C over R. Okay, same thing. Okay, this is tangent of phi, and Imax, I know how much Imax is. Imax is equal to, what is it? It's equal to Vmax divided by Z, where Z is equal to the square root of R squared plus omega L minus 1 over omega C, the whole thing squared, and then the square root. Okay, very good. So we have everything in here so far that we know of. Now I need to find the power. The power then, the power at that moment. So the power is going to be a function of time because everybody is a function of time. So it's going to be the EMF, which is a function of time, times the current, which is a function of time. Everybody is a function of time. Okay. So if I multiply the signs, I will have a sine squared, not sine squared, because these two signs don't necessarily have the same phase. So this is how this expression look like. I have an Imax times a Vmax, and that is fine, where Imax and Vmax are actually related by this expression, Vmax over Z, times a sine of omega t, sine of omega t plus phi. This is where the trouble is. So this power looks like it's changing with time. If this term is positive and this term is positive, the whole thing is positive. If this term is negative and this term is positive, the whole thing is negative. If this term is positive and this term is negative, the whole thing is negative. If this term is negative and this term is negative, the whole thing is actually positive. So this power could go anywhere it wants to, positive and negative. So sometimes we're draining power from the system and sometimes we're putting it back. So we don't know basically. So this power is time dependent, okay? Let's rearrange this expression in here to see exactly what's going on. So I know that sine of alpha plus beta is sine of alpha cosine of beta. In other words, I'm using trig here to help me out to figure out what this thing is there, times cosine of alpha sine of beta, okay? So I'm going to use this here and rewrite my expression for the power. So the power looks like now as a function of time as first of all, V max I max times sine of omega t, that has nothing to do with that, times sine of omega t cosine of phi plus in here cosine of omega t sine of phi, close the parentheses. Well, I have a sine times sine, so it's going to be sine squared. Then I have a sine times cosine. That's going to be a sine times cosine. Okay. There is another identity that I can take advantage of immediately after I write that one. So let me write two of them actually that I need to take advantage of how to write this expression. I max times sine of, I'm sorry, let me write this one since it's a constant number anyway. Cosine of phi is just cosine of phi. Cosine of phi, as a matter of fact, if you use to go back into that triangle, let me look at the cosine of phi. Here, cosine of this angle is the adjacent over the hypotenuse. The hypotenuse is z times I, and the adjacent is actually r. So cosine of phi from this geometry is equal to r, which is the adjacent times I, divided by z times I. So it's r over z. As a matter of fact, I can also find sine of phi. It's clearly from this geometry xl minus xc, or omega L minus omega C divided by the same Z. Okay, this is from this geometry, that's all. Because this length is Z times I, and this length is R times I, and R times divided by I divided by Z gives me basically cosine of phi. And sine of phi would be the whole thing in front, which is XL minus XR, XL minus XC, divided by Z also, by the hypotenuse whose length is Z. Okay? So that probably I need them in here. So but it's constant, in other words, it's just R over Z, and Z is constant, square root of whatever you have in there. So let's put the cosine phi in here, out of the box in here. Cosine of phi times, I'm sorry, I don't need to write parentheses in here. Sine times sine, that's sine squared actually of omega t, plus, here is where I need to write stuff, plus the same thing in here, I have a sine of phi times sine times cosine. So sine omega t, cosine omega t. Here is the identities that I need in here. I need to find how sine squared of omega can be written in a fashion that is linear. I know that cosine of 2 omega t is equal to actually 1 minus 2 times sine squared of omega t. From here, I have a condition on how to find sine squared. So I can replace sine squared by 1 minus cosine of 2 omega t divided by 2. So I can use this expression in here. And I also know how to handle sine of omega t, cosine of omega t. There is another identity that I know also, which is sine of 2 omega t is equal to simply 2 times sine of omega t cosine of omega t. So those are the two identities that I'm going to use. In other words, this sine is just half of that 2 sines. Now I'm going to find the average value of the power. So P average. I know it's going up and down all over the place, but it's going at the rate of omega. Basically, it changes values 60 times at least from this signal in 1 second. So it matters at the end, it's average. So what the average is going to be defined as the 1 over a whole period of the sum from the entire period of this power. So this is by definition the average over a whole cycle. Remember, it goes very fast in 1 second. So that's what justifies this average in here. So the average in here over a whole cycle. Okay. So let's do this math in here. So let's go back in here and try to average these things. Have you guys seen this expression before? Averaging sine squared and these things, no?
Not recently. It's been a while
Okay.
since I've seen it, but yeah.
Okay, so let's do this average in here. So p squared is equal to, remember that t and omega are related in such a way that they are equal to 2 pi. In other words, t is equal to 2 pi over omega and omega is equal to 2 pi over t. Okay, remember that expression. So I'm going to sub the values in here. So Vmax and Imax are constants. Open parenthesis, constant, cos of phi is also constant, times 1 over t, the integral from 0 to t, and I'm going to sub the value right away. I have a sine squared in here, and sine squared is equal to 1 minus cosine of 2 omega t divided by 2. So it's 1 minus 2 cosine of 2 omega t divided by t, I'm sorry, dt. That takes care of the first average in here. The second average, I have a sine of phi, which is also constant. So I have a sine of phi plus sine of phi divided by t, the integral from 0 to t, and I have a 2 in the denominator also. But in this case, it's just sine of 2 omega t dt. Okay. What's the integral of a sine? It's a cosine. But don't forget, they have to divide by 2 omega t. So you have negative, so the last term in here. So this term, when I integrate it, it's going to be negative 1 over 2 omega cosine of 2 omega t evaluated between 0 and t. For 0, this is 1. So the lower limit is 1. The upper limit is cosine of 2 times omega t. And omega t is actually 2 pi. Okay? And cosine of 2 pi, 2 times 2 pi, that's cosine of 4 pi. The whole thing is actually equal to 1. So you end up with 1 minus 1, and this whole integral becomes 0. So this term in here gives me 0 average. Because the sine function is going to change over this cycle. Sometimes it's positive, sometimes it's negative, sometimes it's positive, sometimes it's negative, sometimes it's positive over 4 periods, because this is actually, 2 periods, because this is, I have a 2 in here, 2 times 2 pi. So in all the whole thing in here, this positive area, which is that's what the integral is, cancels this negative area and this positive area. So this is actually an extra one. So this is just 2 periods. And this is the other one. So at the end, the positive areas cancel the negative areas, and I'm down to exactly where we need to be. So at this point in here, that's why it's 0. The same reason in here also is going to give me 0, because I will have a cosine of 2 omega t divided by, when I integrate, it's going to be a sine. So it's going to be a sine of 2 omega t. So when you integrate, the cosine is going to give you a sine. And it's going to be evaluated between 0 and t. And again, in the lower limit, sine of 0 is 0. And the upper limit, I'm dealing with a sine of 2 times omega t, where omega t is actually 2 pi. Times 2, that's 4 pi. And a sine of 4 pi is sine of 720, and that 2 is 0. So we'll end up with 0 minus 0. So this integral is actually 0 too. This portion of the integral only. Okay? And I'm left with the integral of 1/2 dt. And 1/2 dt is just t. Evaluated between 0 and t, and that is big T. Big T cancels the t, and this is the final answer. So the average power then is going to be, first of all, don't forget Vmax, Imax. And don't forget the cosine phi. And I'm left with, in this case, basically 1 over t times t over 2. That 2 doesn't go away in the denominator here. So it's 1/2 dt evaluated between 0 and t, and that is t. Cancel the t now. And that's good, because the average should not depend on the frequency of the signal, as long as it's fast enough frequency. So it's gone. So that is my average power. The average power, of course, doesn't depend on time. That's the whole point of averaging, so that you can find what's the average is. So there is definitely a value in here. So let's rewrite this guy in here. This one looks like it's R over Z. That is what this expression is. Imax is actually V max. I'm sorry. Let me express things a little bit better now. V max is Z times Imax. That's what we defined. I max is equal to actually the V max over Z. So this expression is Z times I max. And this I found it up there to be actually R over the Z. And this one is I max. Cancel the Z with the Z, and I have a factor of 1/2 in here that survives the whole thing in here. And the power on average looks awfully similar to R times I max squared, with the exception I have this 1/2. If somehow I can push, how are we doing on time? We still have time, no? Give us about 5 more minutes, okay? And I will be done, I promise, because it's critical that hopefully you got it, okay? So this is the expression that we have in here. So what I'm doing in here, it looks like the DC circuit. It is not. This is on average. Let me show you what the DC circuit is. It's Ri squared for a resistor. This looks, it's an Ri squared, except I have that nagging factor of 2. So what I'm going to do in here, I'm going to push it inside the Imax and define a new quantity called the RMS. RMS is by definition Imax over square root of 2. If I do it this way, this looks like this. The average power then is just R times IRMS squared. Okay? In other words, instead of talking about the amplitude of the current, we're talking about the root mean square. So this is the square root, mean, and this is root. That means take the square root. Because this whole operation, basically, was squaring the signal. That's where you get this sine squared to begin with stuff, okay? And then taking the average, which I define it to be this way. And after that, I'm taking the square root because I just want the IRMS. I don't want the IRMS squared. Now it gives me IRMS squared. So it looks very similar to an ohmic circuit. So this is the ohmic dissipation of energy, basically. That's the resistance, basically. Okay. So from this point on, instead of talking about V maxes and R maxes, we're going to talk about the VRMS. So VRMS in the same fashion, I could express it in terms of the voltage, by the way, the same expression is V max divided by square root of 2. This is in the United States. In the US, it's 120 volts, which means the maximum voltage in the United States is not 120. V max actually in the United States is square root of 2 times VRMS. And this is about 170 volts. So the signal that you have in your household goes between negative 170 and a positive 170. So it's a fluctuating. As an effective voltage, as an equivalent voltage to a DC circuit, it's behaving like 120 volts. So that is where the 120 volt is coming from. In the rest of the world, they use 240 volts, which means puts the RMS at around 340 volts. The max value of 340 volt, value evaluating between negative 340 and positive 340. Okay. So this is basically the content for this chapter. You have to attend and do the problems. Otherwise, you're taking a big risk because these concepts are heavy stuff. Okay. These things are extremely not light at all. So I suggest to see you guys on Thursday. Hopefully live, Tuesday live, okay, where you actually do these problems. And don't forget, we have a lab this afternoon, so I'll see you at 5 anyway, okay? So I'm gonna stop sharing the screen. Stop recording, I'm sorry, okay? And then I'll see you later. Sounds good?
Sounds good. Oh, right, I might come in a little late because I'll be driving on my way home. So as soon as I get home, I will log on for the lab and everything.
If you miss anything part of the lab, you really have to go back into it, honestly, because there will be a lot of this stuff. So I hope that you guys will not miss anything in their lab too, because it's a big lab too. 2 labs. Okay.
Right.
See you. Take care.
All right. Same to you. See you later.